Alright, in this video we are going to continue to discuss directional derivatives, but maybe make our lives a little bit easier than always computing limits. There's a nice theorem in the textbook that offers us a way out of limits and that limit definition. And it's theorem 6.2. I call it the Big Theorem just because it is really big and it's really nice. The idea is that you still have to have f defined in the same manner, so on a domain D and Rn going to R, da 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 da, but we also must assume that f is differentiable at A, and this, again, this is bold, so that's a vector. Okay, then we can say that the directional derivative, okay, so we learned that notation last time, at A, right, is equal to the gradient of f at A dotted with, this is not multiplication, this is a dot product, okay, dotted with the vector that we are progressing in the direction of. Okay, this proof isn't too bad. You should use a limit definition of the derivative. I'll say so. Limit definition of the derivative. So remember that grand theorem. That was for Rn to Rm. There was a preceding theorem that we did that was just Rn to R, and use that definition. Ideally, showing that the difference between the function and the tangent plane is 0. Okay, so that's kind of the manner in which you progress. Okay, so now just as a quick example here, we're going to find the directional derivative of that function at that point in the direction of each of those. Okay, so first of all, before I proceed, I like to just make unit vectors right away. So this point, or this vector, okay, so it's a point, I listed as a point, it should probably be listed as a vector. We can do 1 by root 2, comma, negative 1 by root 2. Oh, goodness, let's try that again. And this one should just be 3/5, 4/5. Alrighty, okay. So now, all I have to do is find the gradient at A, dot it with what I had, or with my unit vectors. Okay, so let's just find gradient of f, right? If I do that, let's see what I get. So gradient of f, alright, so this is going to be a vector that is 6xy for the x component, and for y, I believe I get 3x squared minus 3y squared. Yeah? And then if I look at the gradient of f at my point 2, 1, right? I believe I get, let's see, so that'd be 12, comma 9. Okay, and then so I'm going to say next at, let's do 1 root 2, comma negative 1 over root 2. I'm going to say directional derivative with respect to, and let's call this u for shorthand notation, directional derivative in the direction of u of f at 2, 1 is just going to be 12, comma 9 dotted with 1 root over root 2, negative 1 over root, 1 over root 2. Okay, and let's see, if this simplifies, I believe I get just 3 over root 2, which if you need to rationalize, feel free to. Okay, and then similarly at 3/5, 4/5, which, let's call that vector w. I'm going to say directional derivative in the direction of w of f at 2, 1 is equal to 12, comma 9 dotted with 3/5, 4/5. Okay, so let's see, I think that's 36 over 5 added twice, which is just going to be 72 over 5. Okay, and that's all we have to do. So nice shortcut way of finding the directional derivative.